All right. So my project this summer was investigating drivers of subsidence on the Mount St. Helens pumice plain using INSAR. So Mount St. Helens erupted on May 18th, 1980. The eruption began with a magnitude 5.1 earthquake that destabilized the northern flank of the mountain and led to a massive debris flow that swept through the surrounding valleys and into the North Fork Toutle River Valley. It was followed by a series of pyroclastic flows, which mixed with the debris flow, and together they formed the pumice plain, which sits between Mount St. Helens and Johnston Ridge, and that is the area of study for this project. We study the pumice plain using interferometric synthetic aperture radar, which is INSAR. And the way that this works is that we take radar images, which were collected in the same location on different dates, and we can difference them to see how the ground has deformed over that time period. So in the bottom right, you can see two radar images. They're kind of the green looking ones. And then the third image is the interferogram that we get that tells us about the deformation. And we use three different satellites for this: NVSat, ALOS, and Sentinel-1, which were all active during different time periods. They can tell us about how deformation has occurred throughout the past approximately 20 years. Past INSAR studies of the pumice plain have identified an area of subsidence at the base of Johnston Ridge. And so the goal of this study was to investigate what is causing this subsidence. So we look at three possible mechanisms. The first is compaction of pre-eruption sediment. So sediment that was in place before the eruption could be compacted by the weight of the overlying debris flow deposit, and this could lead to subduction or subsidence over time. If this were the case, you would expect a fairly consistent subsidence signal throughout the past 40 years, and you would expect it to be proportional to the thickness of the debris flow deposit. The second possible mechanism is melting of buried glacial ice. So Mount St. Helens was pretty heavily glaciated prior to the eruption, and a lot of that glacial ice was removed in the initial debris flow. So ice that remained unmelted could have been buried and insulated by the overlying debris flow deposit and be slowly melting out over time and causing that subsidence. If that were the case, you might expect to see some drainage channels for the water that was draining out. And you also might expect to see sort of a patchier subsidence signal due to ice being buried in different locations, as well as different rates of subsidence based on the size of the melting ice pieces. The third possible mechanism is dewatering of a saturated deposit, which is similar, but rather than the ice having survived the eruption, you would have had melted ice that resulted in a heavily saturated debris flow. And in this case, you would expect those similar drainage channels from water draining out, but you would expect maybe a little bit more of a consistent signal across the pumice plain due to a well-mixed and more homogeneous debris flow deposit. So what does the INSAR actually show us? These are three of the displacement maps that we created. So as you can see, the blue represents subsidence, and the total area of subsidence is about 4.5 square kilometers. And you can see that it occurs in these two sort of lobes. So in the top left image, the subsidence is shifted more towards the left along that drainage channel. And in the top right image, you can see that it's more off to the right. So those are what we call the eastern and western lobes. And both are present in the more recent Sentinel image at the bottom. What's interesting is that the eastern lobe has been increasing in the rate of subsidence, whereas the western lobe has been decreasing over time. We also wanted to make sure that these signals were real subsidence signals rather than just INSAR processing artifacts. So we differenced digital elevation models from 2009 and 2017, and also 2009 and 2002. And what we can see from that is that this same pattern of subsidence is present, which is a good indication that these are real signals rather than processing artifacts. So what does this tell us? Well, of the three theories, we think that the most likely is melting of buried glacial ice. This is because of the patchiness of the subsidence signals and the different rates of subsidence that we see across the pumice plain. But it's also possible that the third mechanism, dewatering of a saturated deposit, is involved, because you can still see those drainage channels and it's difficult to differentiate from just remotely sensed data. So something like a ground penetrating radar survey or a sediment core could be another way to help differentiate in the future. And these are my acknowledgements. Thank you.
Fantastic. Good job, Michela. Okay, questions? Yes, Jess.
Hi, that was excellent, Michela. Great job. I had a question. Did you, in all of the INSAR visuals that you looked at, did you notice any seasonality to it? As far as like, was there melting at any one point of the, at any points in the year that were more so than any others?
Yeah, so that was something that I wasn't able to look at just due to the availability of radar images. There weren't really enough pairs. You need like approximately 10 pairs to make a good stack of interferograms. And if you don't have that many, then there's a lot of like error caused by atmospheric noise. So I wasn't able to look on that short of a time scale. But I think with Sentinel data, you might be able to. So that would be something interesting to look at in the future.
Cool, thanks.
Yeah.
Any other questions?
Anika, there's one in the chat.
Ooh, thank you. Scott would like to know, is there any kind of groundwater flow model or prediction whether water might be able to infiltrate without producing drainage channels, or are the drainage channels apparent?
So you can definitely see drainage channels. If you look, there's a pretty high resolution, so 1 meter DEM, and there's an accompanying hillshade map, and you can see the drainage channels pretty clearly in that, but I haven't looked into modeling any of the drainage or anything like that, but that would be interesting.
Enrique.
Nice job. This is my mentee, I suppose, for communications and writing. My question, and I think maybe I've asked you this before, is about the approximate depth of the deposit. I know that you said that GPR or sediment cores could help you get at that, but has there been any work whatsoever to see, even maybe like seismically, if you can get at how thick the deposit is? Or do you have any kind of estimate, even from outcrops?
Yeah, I wasn't able to find, that's something that I looked for, like a map of the thickness of the debris flow deposit, and I wasn't able to find one. I think there are like certain spots where they know the thickness, but that was something that I tried to find and couldn't, although it might be out there. I'm not sure.
I guess a follow-up is, do you happen to know how much the topography prior to the deposition changes? Because it probably, the deposit thickness may vary, due to that.
Yeah, so there are a couple of DEMs from before the eruption, but they're very, very coarse resolution. So it's pretty hard to tell much about like the small scale changes, especially it's only like a 4.5 kilometer area where the subsidence is going on. So that's a lot smaller than some of the resolution from the earlier DEMs.
Fair enough. It was in 1980, so.
There. Okay, that's all the time we have for Michela's questions, but if you have more, put them in the chat. She'll read them and get back to you.